about this for a second. Your computer, it's making billions of decisions every single second. Not vague guesses, but hard, concrete, yes or no decisions that run everything you see and do. But here's the paradox, the thing that's kind of wild when you think about it. Computers don't have any intelligence, none, no awareness at all. So how on earth does a machine built on simple on and off switches create our entire complex digital world? Well, that's exactly what we're going to break down.
So that brings up this huge, fundamental question, right? How can a machine that literally cannot think do things that seem so incredibly smart? How does it actually decide anything?
And yeah, this quote from our source material just hits the nail on the head. Inside that box, there is no consciousness, no pondering, no understanding. It's just electricity. So to really get how this all works, we have to strip everything away and go right down to the bare metal.
Okay, so we've got to start at the most basic level possible. I mean, forget about apps, forget about your operating system, forget everything you see on the screen. We need to get down to the only two things a computer actually understands, on and off. And that language is called binary. It's a system that has only two letters in its entire alphabet, a 1 and a 0. The 1 means on, and the 0 means off. Everything, and I mean everything, from the game you're playing, to the music you're listening to this very explainer, it's all just a ridiculously long string of 1s and 0s. So how does a computer physically hold a 1 or a 0? Well, it uses this incredible little invention, the transistor. The easiest way to think of it is as a microscopic light switch. It can be on, letting electricity flow, or it can be off, blocking it. There's no dimmer, no in-between state. And your computer's brain, the CPU, has billions of them. And this is the bridge between a physical world and the abstract world of data. When a transistor has high voltage and current is flowing through it, the computer sees that as the on state. To us, that's a 1. When the voltage is low and the current is blocked, that's off, which we call a 0. That's it. This is the physical reality behind every single piece of information on your computer.
All right, so we have billions of these tiny on-off switches. Kind of boring by themselves, right? A single switch isn't very useful. But what happens when you start wiring them together in very clever patterns? Well, that's when you start to create the actual building blocks of logic. See, these special patterns of connected transistors are called logic gates. This is really the first step up the ladder of complexity, and it's where things start to get really interesting. These aren't just random circuits, they are specifically designed to answer very, very simple questions.
Let's just look at the basic ones. You've got an AND gate. It only outputs a 1, an on signal, if both of its inputs are on. Then there's the OR gate, which is a bit more relaxed. It'll output a 1 if at least one of its inputs is on. And the NOT gate is the simplest of all. It just flips the signal. If you give it a 1, it gives you a 0. These aren't just ideas. They're actual physical circuits that give predictable results based on electricity.
Now here's the next step. You take thousands of these super simple gates and you combine them. By doing that, you can build more complex circuits that can do something that starts to look like a decision. They can compare two binary numbers and answer questions like, is this one bigger than that one? Or are these two numbers the same? This is absolutely crucial. All the complex comparisons your computer makes are built out of these ridiculously simple yes or no logic gates. Okay, so now our computer can tell if one number is bigger than another. That's cool. But how does that turn into, actually doing something, like running a program? Well, that's the next layer, turning all this raw logic into real action. The first thing you've got to realize is that software isn't magic. It's not this mysterious cloud of code. It's really just a recipe, a very, very long and precise list of dead simple instructions like add these two numbers, move this piece of data over there, or compare these two things. That's all a program really is. And the CPU, its entire job is to just follow that recipe, mindlessly, one step at a time, billions of times a second. It does this little 3-step dance, as you can see here. First, it fetches an instruction. Then, it decodes it to figure out what to do. And finally, it executes it, using those logic circuits we talked about. Fetch, decode, execute, over and over and over again. And this is the moment it all clicks. The absolute most powerful instructions in any computer program are these conditional ones, the if-then statements. If the player's health is 0, then show the game over screen. If the password is correct, then grant access.
This is the very heart of what we think of as decision-making. So how does this happen physically? It's genius, really. When a logic circuit makes a comparison, the result, true or false, sets a tiny little switch inside the CPU called a flag. It's like a railroad switch. If that flag gets flipped to a 1, the CPU is physically hardwired to follow instruction path A. If it's a 0, it's forced to follow path B. There's no thinking, no pondering, it just follows the track that the switch is set to. So when you look at any one of these little operations by itself, it seems kind of underwhelming, right? But the magic isn't in the operation itself. The reason computers feel so powerful is because of two things: absolutely unbelievable speed and massive, massive scale. I mean, just look at this number, 4 billion. A modern CPU can run through that fetch, decode, execute cycle 4 billion times every single second. It's almost impossible to comprehend. Each one of those tiny cycles could be another one of those simple if-then decisions. And it's not just about raw one-track speed either. Modern CPUs have what we call multiple cores. You can think of these as separate little brains on the same chip. This means the computer can follow multiple recipes or multiple instruction paths all at the same time, which just multiplies its power. And get this, to squeeze out even more speed, they pull off these wild tricks like branch prediction. It's basically where the CPU guesses which way a decision will go before the answer is even ready. If it guesses right, which it often does based on past patterns, it saves a ton of time. If it guesses wrong, no big deal. It just throws that work away. It's not thinking, it's just playing the odds. But this is probably the most crucial thing to wrap your head around. The CPU has zero clue what it's actually doing. When it's playing music, it doesn't hear music. It's just following instructions to toggle voltages that eventually make a speaker vibrate. When it shows you a photo, it doesn't see a face. It just sees a grid of numbers. All the meaning, all the purpose, that comes from the software, not the hardware. So let's put it all together. What is a computer decision, really? It's just a physical event. A condition is checked by a logic circuit. The result of that check flips a single bit to a 1 or 0. And then the CPU is forced to follow a pre-written path based on that bit. There is no choice. There is only flawless, high-speed execution. And when you step back, isn't that just incredible? The entire digital world, everything from complex AI to the device you're watching this on right now, is built on this simple foundation. It's an amazing example of how billions of simple on-off switches, following simple rules at an impossible speed, can create behavior that looks and feels intelligent, maybe even a little bit magical. It really makes you wonder, where does that mechanical execution end, and where does true intelligence actually begin?